Professor Mr. K. Balraj is working as a polymer consultant and teaching fellow in the area of polymer science and engineering at CEG Anna University, Chennai. He has completed AMIE in Electrical Engineering at the Institution of Engineers India, Calcutta and MTech Polymer Science and Engineering at CEG Anna University. He is also pursuing his doctoral research work in polymer technology. His area of specialization includes polymer rheology, polymer processing, characterization and testing of polymers, polymer blends and composites and insulation technology. He has in-depth experience on plastic properties, testing methods and the relevant standards. He has more than 15 years of teaching experience in polymer science and engineering, including instrumentation in polymer industries, engineering plastics, conducting polymers and rubber technology at CEG Anna University. He has guided more than 30 MTech students in their research projects. He has presented more than 20 research papers in the national and international conferences in the area of polymer science. He has published 10 research papers in the peer-reviewed journals.
Welcome to UGC lecture series in polymer science. In polymer science, we are discussing about polymer rheology. In the last 3 parts, we have been discussing about what is meant by rheology, what is viscosity, and how viscosity is going to affect the polymer processing. In today's class, we will discuss about what is meant by elasticity, visco-elasticity, and then the different approaches taken in describing these viscous and elastic properties. What is elasticity? In elasticity, the deformation is reversible deformation. That is, when load, forces or constraints are released, the body returns to its original configuration both in shape as well as the size. Elastic deformation can be caused by tension force or compressive force or by shear force. Usually in metals and ceramics, elastic deformation is seen at low strains, that is in the order 10⁻³ . The elastic behavior of metals and ceramics is usually linear. The curve is linear because of the low strain rate. Elasticity could also be non-linear, which is observed in elastomers or in polymers. So, for example, a linear deformation takes place in aluminum when it is deformed at very small strain, whereas for a elastomer or a polymer or a rubber, the deformation is non-linear. The deformation could also be of 2 types. One is permanent deformation, which is in case of plastic or polymeric materials. The other one is recoverable deformation, which is called as elastic. Both the plastic and elastic deformation can exhibit instantaneous deformation or time dependent deformation, and the time dependent deformation could be anelasticity or viscoelasticity. Now we will come to discuss about what is meant by viscoelastic state, a state being viscoelastic. Why this viscoelastic occurs in polymers? Because of the entanglement of the molecules. Thermoplastic materials have different properties compared to other materials like metals. In the earlier episodes, we have discussed about entanglement. Entanglement means most complex coiling nature of the polymeric chains. The polymeric chains can slide past each other because they do not share chemical bonds with the other chains around them. Each chain do not have any chemical bonds with the subsequent or neighboring chains. Therefore, polymeric materials have viscoelastic properties, that is, they can stretch, which is elastic, and also they can flow, which is viscous. Now, let us put a load on a metal rod. It will stretch to a certain length. As long as the load does not exceed the yield strength of the rod, when the weight is removed, the rod will return to its original length. This is elastic behavior. If the applied load exceeds this yield strength, the metal may break. If you put a similar load on a plastic rod, it too will stretch. Now, if you remove the load quickly, the rod may return to its original length. But if you leave the load on the rod for a length of time or for an extended period of time, the polymer chains will slide past each other because of the application of the force and may try to flow to make the rod length longer. It looks as though it is stretched, which is called as an increase in strain. The longer the load is applied, the more the rod will length, or in other words, the more the chains will have flowed until the bar ruptures. This cold flow exhibits the viscoelastic nature of thermoplastic materials. Now, two different concepts arise in viscoelasticity. One is creep, another one is stress relaxation. An increase in length with a constant load over time is known as creep. A decrease in stress with a constant strain is known as stress relaxation. Now, in both the cases, what happens is the gravity causes the molecules to flow to relieve the stored stress. We will see what is creep. When a body is loaded or stressed and the stress is held constant, the body continues to deform with time. Now, a constant load is applied at a specified time. Now, you could see the deformation starts increasing with respect to time, which is what called as creep. Next, stress relaxation. When a body is deformed, that is, it is strained and the deformation is held constant. Now, stresses in the body will reduce with time. Because of the strain, because the material is subjected to strain, there will be a deformation, there will be some stress that is stored, and this will reduce with time. Looking into this curve, a constant deformation is maintained, which will result in stress getting reduced over time, which is what is called as stress relaxation. Now, we will see how this combined viscous and elastic behavior is which is typical of polymeric materials. Consider a viscous fluid which is allowed to drop freely at a given height. Now, because of the stored stress or strain or the holding forces, or because of the polymeric entanglements, this will remain its original state. But slowly, because of the gravity force, this may undergo strain or it may elongate. Slowly it may move down. Because of this weight, it will try to reach the bottom surface. If you look into the thickness of this very high, now you are going to give some more time. That is what we call it as relaxation. Now that this is stress relaxation. Now you could see this thickness of this fluid is getting reduced. It is getting reduced further until it ruptures. So finally it will reach a state like this. Or in other words, the gravity tend to release the stress. As a result, the material will start flowing. So this viscous and elastic behavior is a typical of polymeric melts. Now, there are two main things that will affect the viscoelasticity of a plastic part. So that is, a plastic part is a final product which is obtained by various processing technologies like injection molding or extrusion molding. So in all these are the two main things that will decide the final mechanical properties. One is temperature, another one is strain rate. Now, as you increase the temperature, the polymer chains are further apart, or in other words, there is more free volume and can slide past one another more easily. Now, if you increase the strain rate, the polymer chains do not have enough time to flow past one another, and therefore they will break sooner. They get tangled with each other. It is therefore the temperature and strain rate is very important. Now, it is important to remember that viscoelasticity only deals with solidified plastic materials, or in other words, polymeric melts. Once the polymeric pellets or the polymeric powders are heated in a high temperature barrel, it solidifies or it becomes a highly viscous liquid. So that is where the viscoelasticity is important. Now, when the material is molten completely liquid, viscosity here refers to how the chains move in relation to each other. The movement of the chains in viscous state and in viscoelastic state are totally different. The thermoplastic materials have both long and short time properties, that is, they flow due to stress over time. Most mechanical testing of plastic materials is actually testing the material's viscoelasticity. That is, the mechanical properties like tensile strength or compressive strength or shear strength, all these tests are aimed or are conducted to test the viscoelastic nature of the polymeric material, because all the final products properties of the final polymer products will depend on one single most term, which is viscoelasticity. Now, how the plastic flows when different stresses are applied, we will see. Now, the plastics are rate sensitive, that is the stress rate or the strain rate, both the rates. It is important to therefore to understand the viscoelasticity of plastic material, so that one can predict how well they will behave in their intended application. So, by studying the viscoelastic property of the material, so one can easily choose a type of plastic material for a type of application. Now, a good way to understand how these material factors like the inherent physical properties of the polymeric materials is going to affect the viscoelasticity of a polymer is to look how they are commonly tested. Some common mechanical tests performed on most plastic materials are tensile testing and impact testing. So, in a tensile test, a test bar commonly called a dog bone or a dumbbell shape is pulled from one end while the other end is fixed. So, this is a typical test sample which is called a dog bone sample or a dumbbell shaped sample. This is as per American standard test method ASTDM. So, there is a test method for each and every polymeric material which is subjected to a tensile testing. So, in this, the one end of this dumbbell shaped sample is fixed, the other one is applied a force. So, this is a universal testing machine in which we can do the variety of mechanical testing, like the same instrument can be used for tensile test, compressive strength and shear strength. Now, it has two adjustable grips to hold the sample. So, the bottom grip is stationary and the top grip can move, that is it can apply a force to the sample. Now, the sample is clamped in between and then the sample is subject to tensile testing in the direction as shown in this red mark. So, the test machine causes the movable grip to move away from the fixed grip at a constant rate. Now, what is the rate at which the movable grip can move is again specified by the ASTM standards. For example, for rubbery materials you can go up to 20 mm per minute, whereas for a composite specimen it is only around 2 mm per minute. Therefore, this speed rate is the speed rate at which you conduct the test is vital, and it is also specified by the ASTM standards. Now, while the grip is moving away, the equipment measures the force necessary to maintain the constant speed, and this will generate a curve. From that curve one can interpret the mechanical properties. Some of the properties that are gained from this is from these are modulus, yield stress, ultimate elongation and toughness. The curve generated by the universal testing machine is simply the stress strain curve, from which one can obtain the tensile modulus, maximum stress before it ruptures, and then the maximum elongation it can undergo before it ruptures, and then how tough the material is. Now, what is stress? The stress is the load divided by the cross sectional area of the test bar or the test specimen, and the strain is the change in length divided by the initial length. Now, we will see one by one. First, the modulus. The modulus is the slope of the curve in its most linear position or the linear portion or the initial portion. Simply fitting a tangent to the initial portion, that from the slope we can find what is the modulus. So, this is stress and this is the strain. From this ratio one can find what is modulus. In fact, it is the change in stress or change in strain, change in stress by change in strain, the ratio between these two. It is a measure of the stiffness of the material, how stiff the material is. If the material is more stiff, then the curve tends to go more near to the y axis. Next, the yield point. The yield point is taken when the slope of the line is 0 and is sometimes called the zero slope yield, or in other words, from the stress strain curve what is the maximum value it reaches, that is supposed to be the yield point. Now, if you subject it to more stress beyond this yield point, the material may fail. Next, the ultimate elongation is the how far the bar stretched prior to falling. So, therefore, the maximum strain it undergoes is the elongation from so this is the ultimate elongation. Next, the toughness. So most of the times the polymeric products are tested for its toughness, that is for example a plastic PET bottle, when you drop it down from a given height, when it is filled with water, if the plastic bottle does not break, then it shows that the material is more tough. So therefore the toughness is an important property that is evaluated for plastic materials. Toughness could be obtained readily from the stress strain curve. The shaded region, that is the area under the stress strain curve, is going to reflect directly on the toughness of the material, or in other words it is a measure of amount of energy absorbed by the sample before failure. That is, if a sudden impact is given to a material, how much energy it could absorb and then how much energy it could transmit without causing rupture to the material is what we call it as toughness. So from this stress strain curve, simply by measuring this area one can say how tough the material is. Now these are the different stress strain curve, from which we have different classifications like hard and brittle material. If the material is more brittle, that means the ability of the material to transfer the applied impact is less, therefore there will be less elongation, and you could see that of course it has a very high strength, but then the material fails at a very low strain rate. Whereas if the material is hard and strong, then the failure would not take immediately, it may undergo some elongation before it fails. Now if the material is more hard and tough, you could see the area actually increases, the area under the stress strain curve increases. A hard and tough material can transmit the applied impact to the entire matrix of the material. As a result, it can withstand the more forces before it fails, or in other words it will undergo more elongation. If a material is soft and weak, then it will have very low tensile strength, as indicated from this. It has a very low tensile strength if the material is weak, but the weak materials will undergo more elongation or strain. Now if the material is soft and tough, that means its tensile strength is low, but then the material is more tough, or it may try to change its geometry before it fails. So therefore shape of this stress strain curve, one can easily predict the material properties. Now we will see one by one how would the tensile properties change if the temperature were increased. So earlier we have seen temperature and strain rate are the two important things with respect to viscoelasticity. So therefore we will see first, if you increase the temperature, what will happen. So this dotted blue color dotted curve is the original curve. Now this is the curve obtained after increasing the temperature. Now if you increase the temperature, or if you apply more heat energy to the sample, that means there will be more free volume that will allow the chains to flow past each other. As a result, the modulus will decrease. You could see the curve drops down. If the curve drops down, automatically its slope reduces and its modulus increases, and also the yield stress decreases. Compared to this one, you could see here the maximum yield stress is less, but the elongation will increase. If you increase the temperature, what happens is a more solid like polymeric material will become a viscous like fluid. As a result, it may undergo maximum elongation, and because of this the toughness increases. You could see the area under this curve compared to the area under this solid curve. So the toughness increases. So these are the parameters when you increase the temperature. Now why this temperature is important? Because the polymeric materials, when it is processed or when it is converted into a useful shape or into a useful product, the temperature at which it is processed. For example, for polyethylene or polypropylene, a typical set temperature for processing is 200 to 220 degrees Celsius in injection molding machine. Therefore, arriving a suitable temperature is important. Next, how would the tensile properties change if the strain or the test speed were increased? As I told you earlier, in the universal testing machine, you have provision to change the speed at which the movable grip can move. For example, from 2 mm per minute to 5 mm per minute or 20 mm per minute. But again, this test speed were set by the ASTM standards. Now if you, let us see how if this test speed were increased. If the test speed were increased, the polymer chains do not have time to slide past each other. As a result, there will not be any morphological changes inside the polymer sample. So here also you could see this blue dotted curve is the original curve, and then the thick line is the curve obtained after increasing the strain speed. So the modulus will increase, the yield stress will increase because it is more or like the original shape, whereas the elongation will decrease because the material is more rigid, and then the toughness would also decrease. So these are the properties that is affected by change in the speed, test speed. Now how would the tensile properties change if the strain rate or the test speed were increased? Here again the strain rate is the deformation rate or the elongation rate were increased. Now this is what happens to the sample. So this is the first sample. This is the bar run at 1 inch per minute strain rate. So the test speed here is 1 inch per minute. Compared to 20 inch per minute is very less. As a result, you could see the sample gets elongated, or it has undergone more deformation, or there is more strain it has undergone before the material has failed. Now whereas if you test the same sample with 20 inch per minute test speed or the strain rate, you could see there is no elongation or stretching at all. The material has broken instantaneously. This is because the polymer chains do not have sufficient to slide past each other. As a result, there is a brittle failure, and also this failure takes place at the near the neck of this dumbbell shaped sample, whereas you could see the position at which the break has taken is almost 1/4 from this side or from 3/4 from the movable grip side. Another thing is changing the temperature in one direction is similar to changing the test speed in other direction in terms of the material properties, or in other words, if you increase the temperature and if you decrease the test speed, both will result in a similar shape of the curves. These curves go down with the increase in temperature. If you increase the temperature, as we have seen earlier, there is more free volume, so polymer chains can move freely. It can undergo more elongation. So the maximum elongation is undergone by this material, this one. The same way, if you increase the strain rate or the test speed, it is the other way. If you increase the strain rate, the material do not have sufficient time, or the polymeric chains do not have sufficient time to slide past each other. Therefore, it may have high tensile strength or yield strength, but the material will fail. Now let us see how the physical or morphological parameters of the polymeric sample like molecular weight will affect the tensile properties. A high molecular weight will affect some of the properties, but typically the modulus does not change much. As you have seen earlier, the modulus is a parameter which is more related to, or it is the ratio between change in stress by change in strain. As a result, the molecular weight do not have any direct effect on the tensile modulus. Now a high molecular weight increases the entanglement of the polymer chains, which will increase the elongation, toughness and yield strength. So because when the material has high entanglement, then it needs more energy to deform. Therefore, it can withstand more stress. As a result, the elongation will increase. If the elongation increases, then the area under the stress strain curve will increase. Therefore, toughness will also increase, and the yield strength of course will increase slightly. The yield strength depends on whether the material is brittle or the material is soft. If the material is rigid, yield strength will be high, whereas the material is soft, the yield strength will be low. Now the modulus is more dependent on the structure of the molecule. Instead of the molecular weight, it will depend on the structure of the molecule, whether the molecule has any bulky groups like a benzene ring. If a benzene ring or a bulky group is in the main chain, if these bulky groups are substituted as side chains, then that will have a direct effect on modulus, and therefore it will depend less on the entanglement forces. So it is relatively unaffected by longer chain length. So chain length will not have any effect on the modulus, rather the chain modulus will depend more on the structure. So presence of bulky groups like for example polystyrene you have benzene as a pendant side group. So polystyrene has a very high tensile modulus. Normally a polymeric virgin plastic alone is not used to prepare a product. For example, you could see in the day to day life lot of water bottles, plastic water bottles in all different colors like green, red likewise, and then some of the bottles are transparent. So all these are because of the type of filler that is added while it is extruded in a blow molding machine. Now what happens when you add a filler to a plastic material when it is processed? These fillers will hinder the molecular movement and thereby will prevent the molecules from sliding past one another. So this actually puts a brake on the movement of the chains from one chain or another. So these fillers will make the materials also stiffer. This will therefore, if the material becomes more stiff, this will increase modulus and this will also increase yield strength, but this will decrease elongation and toughness. So therefore the amount of the effect of the filler on the properties will depend on what is the type of filler that is added, and depend on amount of filler, what is the type of filler added, and shape and size of the filler particles. This is going to play a vital role in nowadays because people add all these fillers in a nano size for property enhancement. Now next, the morphology. How does the amount of crystallinity affect the tensile properties? All the polymers are not 100% crystalline. So normally polymers are semi-crystalline material. Ideal percent is 60% crystallinity and then 40% it is amorphous. In a semi-crystalline material, higher level of crystallinity will provide a high modulus and yield strength, lower elongation and toughness. That is, a material is more crystalline, then there is more regular molecular arrangement. Therefore, that will automatically will result in a very good modulus, and when you subject it to tensile testing, it will definitely have a very high yield stress. So whenever high modulus and yield stress, then that will automatically reduce the elongation. Therefore, the area of the tensile curve will decrease. Therefore, toughness will also gets reduced. This is because the densely packed crystalline regions prevents the chain from sliding past one another. So this does not necessarily mean that a semi-crystalline material will be stiffer than amorphous material. So therefore, this could not be used as a thumb rule to distinguish between a amorphous and a semi-crystalline material. It is more a matter of the particular type of material's chain structure, whether it is linear or whether it is branched, how dense the polymer is. So therefore, it depends more on that also, and also with respect to its relation to its Tg. Tg is the glass transition temperature of a polymer. Now what will happen when you have a very level of branching? So nowadays polyethylene is available in different forms like low density polyethylene, high density polyethylene, linear low density polyethylene. So in all these the branching rate or the branching ratio differs. Now this is going to have a effect on its tensile properties. Supposing you have more shorter branches, this would result in a higher degree of entanglement, and the material would behave similarly to if you increase the molecular weight. So therefore, short branches is similar to high molecular weight materials, because in both the cases there will be a higher degree of entanglement. Now what happens if you have long branches? Long branches provide more space, you could see in this, between the molecules, and therefore this will reduce the entanglement similarly to if you increase the temperature. So therefore, the effect of temperature or effect of molecular weight could also be achieved by preparing a short branched materials or a long branched materials. Summary. So in today's class, we have started with entanglement and viscoelasticity, and the two main things the viscoelasticity depends on is, one is temperature, another one is the strain rate. So therefore, the temperature and strain rate effect on thermoplastic products is very vital in understanding the viscoelasticity of the polymeric materials. Now in order to understand viscoelasticity, we have discussed about tensile testing, the way the material is subjected to test, from which one could understand the viscoelastic properties. And then we have also discussed about the inherent polymeric factors such as molecular weight, fillers, branching, crystallinity and structure. On all these, how is going to affect the material properties, finally the viscoelasticity. After viewing this episode, viewers are requested to ponder over these questions, that is, what is meant by viscoelasticity? How does changes in temperature and strain rate can affect properties of thermoplastic products, and why viscoelasticity is a fundamental concept in understanding of plastic behavior, and also distinguish between creep and stress relaxation. Thank you.